Hello everyone, my name is Singh. My enrollment number is 25125016 and today I am presenting my C++ project which is a game named Forest Quest. This isn't a game about graphics, it's a world built entirely by C++ logic and data structures. While making the game, my primary objective was to master the fundamentals of C++ by building a functioning game state engine. The project is a hands-on demonstration of data modeling, showing how complex rules can be enforced using simple C++ features rather than relying on external libraries or other graphic engines. My game, Forest Quest, is a classic text adventure or interactive fiction. Our challenge was to create a game that is responsive and rule-bound. The entire experience runs on a simple loop. The code describes the room and waits for your command and then updates the state accordingly. Every command you type must be validated by the code. The game's goal is straightforward but unforgiving. You have to find the gear and defeat the skeletal guardian. The path is protected by two critical puzzles that test the game's logic. The first is the lock puzzle, which includes the key and the chest. The second is the lethal zone. This is where our rules are absolute. The code is designed to instantly kill the player upon entering the ruins if two Boolean conditions are not met. If you have, you must have the oil lamp and the fine sword. If either is missing, the quest ends, demonstrating strict logic enforcement. Before we dive into the blueprints, let's establish the toolkit. My project relies heavily on C++ standard template libraries, STL. Every library here serves a critical function that moves us beyond the simple programming. We start with the text fundamentals. String is used for all text data, our description, item names, and player input. Paired with that is unordered map. This is the game's fast database. We use it to store all the room and items using unique ID as a key. This guarantees big of one constant time lookup, which is absolutely essential for quick and responsive data access in any well-designed game. Next, we have a list management. Vector is a primary tool for dynamic lists. It holds the player's inventory and the items in each room, allowing these lists to grow and shrink easily. To operate on this list, we need the algorithm. This library give us high performance logic like we use the find algorithm for quick checks like seeing if the sword is in your inventory or not, and the remove function for efficient consumption logic like we use for the potion one. Finally, at last, a small but important utility of CMath. We don't use it for complex trigonometry, but for simple min function. We need min function in our healing logic to safely cap the player's HP, ensuring they never heal past their max HP. Every tool, no matter how small, plays a role in keeping the game logic sound, like for the CMath. Moving on, to make this game work, we rely on three main technical pillars. The first is a flexible input. We use specialized helper function to process messy inputs like take oil lamp written all in upper cases with spaces in between them and reliably convert them into a clean command. To do this, we define a small helper function normalize id underscore id, which is essential. Its job is to take whatever the player types, like oil lamp, as I said before, with upper cases and spaces in between them, or add having exclamation mark or question mark, and turn it into perfectly clean, standardized code word like oil lamp with all the letters of the word in lower cases with having no spaces in between them and removing the question mark or exclamation mark things. This makes the game case insensitive and prevent typos from crashing our logic. We start by creating an empty string called result in the code to hold a final clean output. We then use a range-based for loop to look at every single character C in the player's input string one by one. In the for loop, the first check handles the capitalization. We ask, is the character an uppercase or uppercase letter? Like we can see here, we are say type here in the code. We can see that we are using that C greater than equals to capital A. Here we are basically comparing the character C with the ASCII value of the capital A. So if it is in the uppercase letter, we perform a simple ASCII trick to convert into a lowercase. We don't need a large library. We just fix the numerical difference between the uppercase letter like capital A and its lowercase counterpart to shift the character down. Now, the second check is the filtering step, and it's vital for cleaning the string. We ask, is the character a lowercase, a digit, or an underscore? This filter is set up using these OR operators. If the character passes any of these three checks, we use the result dot push back C to add it to our final string. Anything that fails in this check, like a space, a question mark, or an exclamation point, is simply ignored and left out of the string. This ensures the final return string is perfectly clean and ready for the game logic to successfully match against our internal item IDs, which we will define fully. This ensures the final return string is perfectly clean and ready for the game logic to successfully match against our internal item IDs, which we will discuss later. Next is the normalization step. This process starts with normalization. This is a critical cleaning stage. Before a game process any command, we call the normalize underscore ID on both the verb, which is the command, and the argument arg. This ensures that if the player types use or take, the input is cleanly converted to lowercase and stripped of the spaces. This prevents errors and make the game case insensitive. After that, we do the flexible search goal. The search goal is simple to translate a vague player request like key into a specific internal ID, rust underscore key. We don't we don't just check for the exact match, we check for flexibility here. The code then loops every item ID in the player's inventory, performing two strong checks for each item. Check 1 is the item ID search. We check in this item ID search, we check if the player's argument is substrings of the item's internal ID. For example, if the player types key, this finds a match within the ID rust underscore key and returns it immediately. Point and check 2 is display name search. This check makes the game even more intuitive. We normalize the item's full display name like health potion written with spaces and uppercases to health potion in the lower cases without any spaces and check if the player's input is a substring of the name. And this is what allows a player's typing potion to successfully find the item even if the game calls it a health potion. By passing either of these two checks which we have written in the loop, the function successfully returns the item's unique ID, which the game then uses to execute the correct action, whether it's using a potion or swinging a sword or anything else. Now, the next pillar is the state management. Every change from reducing the HP to clearing the lock is controlled by modifying simple variables within our C++ structure. Now, the last pillar is and the last pillar is the rule enforcement. Here we can see the example of that. Here in this code, we can see that it says that if room underscore next ID equals to ruins, this is the final checkpoint in our move function, which we will be discussing later. Here, the logic, here it is the logic that prevents the player from winning the game unprepared. Like if here the code asks First ask, is the player attempting to enter the room? If yes, we proceed to check the required conditions for the survival. And if the player does not have the lamp and the fine sword, and the last pillar is the rule enforcement. An example of that is we can see here in the move function, which is the final checkpoint in the move function. It is the logic that prevents the player from winning the game unprepared. The code first asks, is the player attempting to enter the ruins? If yes, we proceed to check the required conditions for the survival. It checks if the player dot lamp is lit is false, or it has the has item function find sword is false. If any of these comes out to be false, we print see out that you stumble into the ruins unprepared and the skeleton guardian senses your weakness and strikes you down instantly. After that, it returns the player's .hp equals to 0 and see out that you died instantly as the player's healing points is 0 and game over, and the running boolean to false and return. The running boolean is false, so the loop ends and we return so that further codes won't run. The last is the last main pillar is the rule enforcement. For an example of that is we can see here in the move function, which is the final checkpoint in our move function. It's the logic that prevents the player from winning the game unprepared. Here, the code first asks, is the player attempting to enter the rooms? If the answer is yes, we proceed to check the required condition for survival. Here, this if function, it is the key line. This is a multi-conditional check using the OR operator. The logic is absolutely unforgiving. The players must not be missing the lamp, which is this, and and must not be missing the fine sword, which we can see by using this has item function. This statement is read as if the lamp is not lit or the player does not have the fine sword, then the condition is true and the trap is sprung. It see out this. You stumble into the ruins unprepared, and the skeleton guardian senses your weakness and strikes you down. Now, if the condition is true, meaning that the player is unprepared, which means that it does not have the lamp or the fine sword, the following lines, these three lines, will execute the failure state, which is first that player.hp equals to 0, which means that this sets the health to 0, confirming defeat, and then running equals to false. This immediately breaks the main game loop, ending the game right here, and at the last return, this exits the function, preventing any further code from running. This small block of code demonstrates how complex game difficulty is enforced using clear logical checks against the simple boolean and the item state variables we define in our structure. Now, moving on. Before we look at the room code, we need to understand the fundamental C++ tool which we use to build the world, the structure. The struct is simply a custom data blueprint. Think of it as a container that allows us to group related variables of different types together under one single and meaningful name instead of tracking 15 separate variables like room underscore name, room underscore HP, and room underscore exit underscore not. We bundle them all into a one neat package. It's basically like imagine building a custom customer profile. You need a string for the name, an integer for the age, and a boolean for status. A struct lets you define that profile once. In the forest quiz, every time we use struct, we are creating a unique object that replaces a visual element. Like the room struct replaces the graphic environment, the item struct replaces the physical object, and the player struct replaces the user profile. This is the data modeling foundation of the entire game's architecture. Now, we will begin with the core data model, the structure room, the foundational blueprint that replaces our graphical map. Here we have defined the string ID, which is the room's unique code name for the computer to use, while the string name is the display title. Now, we provide user experience through basically two texts. The long description, which is for the full detailed first entry when the player is entering for the first time, and the short description for the brief reminder, which is controlled by the visited flag, here which we have defined. The most critical piece is the navigation map, which is the unordered map which we have defined here. This map instantly link a direction like north to the to next room's ID, which is the secret to the fast movement. Now these bold dark flag or string lock target, these fields are of puzzle switches. Like the bold dark flag, for example, is checked by the move function, which we will be discussing later, to determine the path should be blocked. To determine if the path should be blocked or not. And the lock target identifies the object that needs a key. Now, finally, in the last few lines in our room, we are dedicated to combat, for these are only populated for the ruins room, but they show how we integrate the fight mechanics directly into the location data. The string enemy ID holds the unique name of the enemy present, like the skeleton, and the enemy HP tracks the enemy's current health. This is a dynamic value that the attack function, which we will also discuss later, directly reduces. The enemy damage sets the amount of damage the enemy deals back to the player on its turn. These simple integral fields provide all the necessary stats for a turn-based combat system. Now, next we have the blueprints of item and player. The item is defined by its ID, which is once again the item's unique internal code, and the name. Its behavior is controlled by the simple Boolean flags like usable or takeable. Like we use usable if the item is usable in that room, or takeable if checks if that the item is takeable or not. Now, the tracks our dynamic state. It holds our health HP, which is HP, and max HP, which is the maximum healing points which the player can have, and the current list of possessions in the inventory. We have defined here the vector string inventory, which holds all the items the player have at that point. And we use a vector for inventory because it needs to grow or shrink easily as we take or use the item and then remove it from our inventory. The lamp is blade flag is a simple but powerful global switch. When the player uses the lamp, this one Boolean variables, which is right now defined as false, flips to true and globally resolves the darkness barrier in the dark room. Finally, all the modifications to the player struct are handled directly by the internal function, so showcasing efficient pass by reference access. Now, since we aren't using a traditional database, we rely entirely on the STL for storage. We have also discussed this part later in previous, but let's see once again. The unordered map acts as our game's instant database. We use it to store both master list of all the rooms and items. And we have also discussed that it has a constant time access, which is big of one complexity, meaning finding a room is instantaneous regardless of map size. Like if either you have 10 rooms or 1,000 rooms, it takes same amount of time, which is critical for smooth gameplay. And the next one is the vector, which we have also discussed earlier, is used for the dynamic list, like specifically the player's inventory and the items in the room. Vector allows the list to grow using pushback when the items are acquired and shrink efficiently using the erase remove idiom when the items are consumed, like the healing like the health potion. This division of labor between the static map and the dynamic labor is fundamental to the code efficient architecture. Now, input handling and normalization. This is a system that turns messy player typings into an actionable code. We use a command pipeline starting in the run loop First, we capture the entire raw line using the getLine cin line, and we perform the phrasing by using the find algorithm and the substrate to instantly slice the input into the command and the argument, which we can see here in this loop. First, we define the string command and array, then we find the space, and if the space is found, then the command, then we take input in the command like the line and substrate till 0 to the space which where we have found the space, and after that we store other parts in the argument from the space plus 1. After that, the next step is normalization. The normalize ID function cleans the argument by converting it into a lower case and removing the spaces. And this process makes the entire game case insensitive and robust against the typos. The clean command is then routed through the if-else-if chain, and the clean argument is passed to the action functions. This pipeline allows the flexible command like take key to successfully translate and find the internal item ID like rust underscore key. Here we can see the command processing, which we have discussed right now. If the if-else-if chain, like if command equals to look or command equals to else, then the showroom function will run. Else, if the command equals to help or command equals to h, the do help will run, and so on. And else, if all these things are not found in the user input, then it will see out I don't understand the command and type help for the further need. Now we will discuss the action logic of a code of the game. The first is the move function. The move function is the ultimate gatekeeper. It enforces all game's movement, rules, and traps. First, we will check if the destination is valid at all. Like it start with a simple validity check, stopping the function if the player types any invalid invalid exit. Like here we can see it see outs you can't go that way. Now the code enforces the dark wood block by checking the destination room's dark flag and the player lamp is lit status. If the lamp is off, the movement is immediately blocked and the player must use the lamp. Like here you can see out the path is pitch black and you can't proceed without the lamp. Now moving on is when the next room ID equals to ruins. The most critical logic is this, which is the ruins lethal trap. The condition checks if the player is missing the lamp or the sword. If either fails, the code executes instant death by changing the player's .hp equals to 0 and the boolean running equals to false. If the move is safe, the player's location is updated and the function concludes by checking the new room for the enemy and printing the attack alert, which we can see here in these two codes. Like if the next room dot enemy HP is greater than 0, it counts the attention and the next room enemy ID and stand before you and you must attack. The move function is ultimate gatekeeper in a game. Its job is to strictly enforce all the movement rules and traps we built into the world. First, it must verify if the player's path is valid and check for the barriers and confirm the survival condition before allowing. The function starts by retrieving a reference to the current room. It cleans the direction input using normalized ID and performs the basic validity check, which is if the condition is not found in the room's exit map, the movement is instantly blocked and it counts you can't go that way. Next, the code enforces the dark wood block. It checks if the destination is in the dark woods and if the player lamp is lit, flag is false. If both are true, it prints the pitch black message, which is the path is pitch black and you can't move without the lamp and blocks the movement with the return command, enforcing the player to solve the light puzzle. Now, here comes the most crucial logic, which is the ruin's lethal trap. This is an instant death condition. The code checks the destination room and execute the following, which is, and here, the condition for the instant death and the low lamp and sword. If the here you can see if the player dot lamp is lit is false or has item find sword is false. This strict multi-conditional check uses the OR operator to ensure that the player possesses both the lamp and the sword. If either is missing, the code executes the failure by setting the player.hp equals to 0 and running equals to false. And after that, it returns so that the further code won't run. And if the move is safe, the player's location is updated and the function concludes by checking the new room for the enemy and printing the attack alert, which we can see here. Like here, if the next room dot enemy HP is greater than 0, it counts attention, and then the next room dot enemy ID stands before you and you must attack. Our next action logic is the function use. The use function is where the magic of puzzle solving happens. It's the central hub of all item-based action, checking both the player's inventory and their action exact location to decide what rule to break next. The first and the largest block handles the crucial chest unlocking puzzle. This is a complex logic that ensures there, there three things are true. First is that we are at the cottage, which you can see here. The second is the chest is still locked, which you can see r dot lock target equals to chest. And the player is using the key, which you can see here that normalize underscore argument dot find key. After that, it checks if the has item has the rust key in their inventory or not. If it has, then it counts you use the rust key to unlock, its spring opens, and then it if these check passes, we execute the solution. We clear the target string and permanently signaling that the chest is open. Then we add the reward item, the sword, and the potion directly to the cottage item list for for the cottage item list for the player to then pick up. This action modifies the world state, or else we just see out that the chest is locked and it look like it needs a key, so that the player has to find the key. Next is that it checks for the inventory for the item to use. For this, we use the item ID equals to find item in inventory by name. And if the item ID is empty, then it counts that you don't have that item. Next, we have the lamp logic. Using the lamp performs a vital global state change. It says the player dot lamp is list equals to true, flag equals to true. This action permanently resolves the darkness puzzle, allowing the player to safely pass the barrier in the move function. Next, and else if the item ID equals to potion, which it demonstrates the resource management. When the player uses the potion, we increase the player.hp, but we use the minimum function to guarantee that the healing is safely capped at max HP. We immediately follow this up by calling the remove item from inventory, which permanently consumes the resource and deletes the potion from the inventory. Else if the item ID equals to find sword, it counts you ready your find sword, you use the attack command to fight. Or else it shows you can't use and it's out the item's ID dot name here. Next action logic is the attack function. The attack function is the engine for our turn-based combat. It starts with a vital initial check. If the room has no enemy, or if the enemy is already defeated, which is here r dot enemy HP is less than equals to 0. It see outs there is no enemy here to attack the function, and the function stops immediately. We must only run the combat cycle when a live target is present. Now it's the player's turn. This is where the preparation pays off. The code first determines the player damage, which is equals to 0. We deal a base of 1 damage if we are unarmed. However, if the has item find sword check returns true, then we deal significantly higher 5 damage. And here, the if-else block is a crucial difficulty gateway. Once calculated, the damage reduces the enemy's r.enemy HP, and the new health is displayed to the player. Now, the next is the victory check. Immediately after the person strikes, we run this victory check. If the enemy's HP drops to 0, the enemy is defeated. Critically, if this victory occurs in the ruins, the final condition is executed. We set the global flag running equals to false, which terminates the game loop, signaling the player has won the entire adventure. But if the enemy survives the player's attack, it retaliates. That starts the enemy's turn. The enemy deals the enemy deals its fixed damage, R dot enemy damage, which is 5, back to the player, reducing the player dot HP. When we display the player's remaining health, if enemy survive the player's attack, it retaliates. This starts the enemy turn. The enemy deal its fixed damage back to the player, reducing the player dot HP. We then display the player's remaining health. As we can see here, it's out R and R dot enemy ID, which could be skeleton or anything else, attack you for the enemy damage which it does damage, and after that your current HP. And after that, finally, the defeat check run. If the player's HP dropped to 0 after the enemy's attack, the function prints the game over message and sets the running equals to false once again. This shows that both the win and lose condition use the same robust mechanism to end the game. These final slides cover the essential support logic helper that make the main command efficient. Functions like these find item in room by name, which we have discussed this code earlier, or moving on. The the has item function, which uses highly the efficient find algorithm to check the inventory requirement, which we can see here. And finally, the remove item from inventory, which ensures safe resource consumption like the potion by using the erase remove idiom, which is the standard efficient C++ method to deleting the element from a vector. Like if we have used the potion, then it will remove that from the player's inventory. Now, to conclude the technical deep dive and prove all the C++ logic truly works together, I am going to run the game live and solve the entire quest, showcasing the functionality of every major command we have discussed so far. Before running the code, let's look at a code first. Like here we have included all those libraries. After that, we have used the normalize ID to change the user's input into the lower cases. And then we have defined a item structure. After that, we have defined the room structure, then the player structure, and then we have defined a class game in which in private we have defined the player, and then these unordered map and the bool. After that, we have defined some functions whose bodies will be defined later. After that, we have defined the helper functions, and then the take function, which we have already discussed. And then we'll just define the show inventory function. And in this, if the player dot inventory equals to empty, it counts that your inventory is empty. Else it counts the inventory and all the items which are in the player's inventory, which the player has taken using the take function. Now in public, we have defined the void run function in which we have included the show banner, init world, and showroom functions from the private one. After that, we have discussed this part via the string command one, and then we have the command processing part. And after this, now here in the class game, we have defined the show banner function. This function runs at the very first when the run function is started. After that, we have defined the helper implementations, which we have already discussed. Now, we will discuss the init world function, which is defined in the class game. The init world function is like the engine's initial setup phase. It transforms the empty game object into a fully formed, a rule-bound world, and it runs automatically right before the player begins the adventure. Here, the first section populates a private items map we are using the item's unique ID, which is the lamp, and as the key, and assigning the full item structure as the value. This defines all the lamps, all the objects, and the objects the player will encounter, such as the rust underscore key and the final weapon, the fine underscore sword. We also get a critical flag here, like defining if an item is usable or not. This is the most here the room. This is the most critical section as it builds the physical layout and establishes all the rules. For every room, we assign a complete room structure defining its description and its exits map, which connects the locations. More importantly, this is where the game's difficulty is encoded. We set the dark equals to true flag for the dark woods here. We can see to activate the darkness barrier. The cottage is set with the room with the lock target equals to chest to activate the key puzzle, and the ruins room is assigned with enemy ID, enemy HP 15, and enemy damage 5, integrating the final combat encounter directly into the location's data. And finally, the function configures the starting condition for the player object. Sets initial location to the clearing ID and ensures the player's health, which is HP, is set to maximum value, max HP. So they start their quest fully prepared. And in summary, we can say that the init world is one-time setup that guarantees the entire virtual world is structurally sound and ready for the run loop to begin. Now comes the showroom function. Sorry, before that we will discuss the do help. The do help function is critical for user experience, especially in a text-based game. It provides a clear guide how to play without revealing the solution. The function simply prints a large block of static text, but this block is carefully organized as you can see. It separates the basic instruction the available commands from the ultimate goal of the game. This list explicitly states the verb look go and any valid aliases like ln and ln or anything else. This address the flexible input we built into the run loop, informing the player about the shortcuts they can use. Here we can see that look L and go that. Now, the showroom function is we will be defining the showroom function. The showroom function is the player's main view into the game. Its job is to read all the relevant data, the room, the player's state, and the enemy's condition, and the format it for the console. It begins by retrieving a reference to the current room R. This allows the function to access the room's data efficiently. Here, the first and the most important check is the darkness filter. If the room is marked as dark and the player's lamp is not lit, the code prints pitch black message and skips the entire display logic below it. This perfectly stimulates being unable to see. The next is the description logic. We use the visited flag here to show the full detailed long description only once and then switch to the brief descriptions on all the future visits we will do. This improves the pacing for the player. And finally, the function loops to the rooms list. It prints the item present, available exits, and if a living enemy is present or not. It includes the enemy's name or current HP on the status line, as we can see here. Here, the few things are also defined like if the or.id equals to cottage and the locked target in the room R is not empty, it shouts you can use the rust key to open the chest. And after that, we have defined the move function. We have discussed the whole move function. Like the first is check if the direction is valid or not, and then if check if the destination room is dark woods and if the destination room is ruins and all those conditions. The successful move, and then the intermediate combat encounter. After that, I have written the code for the attack function, which we have already discussed, and then the use. And then here comes our main function where we run the game by game.run. And here comes the main function where we run the run loop so that the game will run. Now let's take a look at the how the game works. I will show you how the code of my game will run. Now let's run the code. Here it shows the banner, and then you are in the scenery forest clearing. Path led north and east. Type L if you are stuck. So now I'll just go to east, and then we are in the cottage. A log wooden chest sits here. You see a lamp and a rust key. So take lamp and take key. After that, I will use the key to open the chest. As you can see, the chest is open now. Now I will take the sword and then take ocean. Now I will go to west, back to the clear. So we are out now back in the clear. Now I'll just go to north, use lamp, and now I will go north once more. As you can see, we reach ancient ruin. A skeleton guardian awaits, and then the enemy here is the skeleton. So now I'll just attack. And as you can see, you swing your fine sword and hit the skeleton. You deal 5 damage. Skeleton HP is right now 10. It starts with 15. So skeleton attacks you for 5 damage and your HP is now 15. So now I will use potion once again. Now if I try to use potion once again, you can see that you don't have that active. Now attack, and now once you want attack, and now it shows that you defeated the skeleton and the ruins are now safe. You have completed the forest adventure. Congratulations. So as you can see, this the code runs properly for my game. Now, to conclude, the project successfully demonstrated the power of struct and the STL map in in building a stable data-driven world. We achieve a robust user-friendly experience through the careful input normalization. Now, the future work will focus on implementing safe and load function using the fstream library for the game persistent and adding some randomization to the comment system for the greater variability. Thank you. This was my project, a game, Forest Quest.